which is well known in approximation theory and actually goes back to, I would say, Lebesgue even, that considers something for the whole class. So begin with the function class. So this is what we are doing. We begin with the function class. Usually it is a smoothness class. And we want to build a Cubature formula which will be nice or optimal for the whole class in the following sense. So we begin with this function class and we define this quantity. So this is supremum over all these arrows. So the Cubature formula is applied to each of these functions. We calculate this arrow, and after that we take the worst case, supremum over the whole this class. So this is the notation for that. So in this notation, lambda stands actually includes also the weights of that formula. If you remember, this Cubature formula is defined by knots, which are the most important thing, and also by weights. As it is written here, we are interested in optimal, and optimization means that we are looking for infimum of all these arrows for the class over the weights and over the knots. So how this is related to the discrepancy? The classical definition of the discrepancy is the following. So we consider d-dimensional characteristic functions of parallel pivots. So this is the definition. So it is a product of univariate characteristic functions. So this is the corresponding characteristic functions of the parallel pivot of a special form with edges parallel to the coordinate axis. And for this one, and this is just a definition of the analog, because the function classes what I will be discussing today, it is convenient, just technically convenient to assume that these are 2π periodic. It's just technical assumption that does not make big difference. So now, if we define, again, this is classical definition of L infinity discrepancy. Sometimes it is called star discrepancy. The following quantity. So this is the integral of the corresponding characteristic function, and this is the application of the Cubature formula, which is designed in the following way. All weights are the same, 1 over m, and we evaluate our function. In this case, it's just counting function because it is a characteristic function of this parallel pivot at the corresponding points, and this is the error of this Cubature formula. So basically, we apply the Cubature formula, this given one with equal weights, to these characteristic functions. And now it is clear that if you consider the class of those characteristic functions, this is the same as to say that we consider this A, because A is a parameterization of the corresponding characteristic function. So this is one-to-one correspondence. And this means that when we are taking this maximum, we can say that we are taking the supremum for over that class. So this means exactly that this discrepancy, as we define, this is the error of the particular Cubature formula with these knots for this class of functions. But actually here is nothing, I would say, interesting, but because it is very natural class, just the change of language in a sense. But there is something which is a little bit deeper than just changing of language. And this will make a connection between the discrepancy and other classes of functions, again, smoothness classes, which are very natural in approximation theory. These classes, in a more or less explicit way, were already mentioned by Michael and by Dmitry Bilek when they talked about Cox-Mahlavka inequality. So, and this will be more explicit definition of these classes. So this is the definition of this function class, which sometimes called function class, the class of functions with dominated mixed derivative. So what is that? We define the kernel, this function. This is univariate function. Then we take a product. And when we take this product, this basically corresponds to taking something, in that case will be integration, with respect to each variable, one after another. And now we define the function class, and M stands here for mixed. So mixed, W stands, actually it's a standard definition for Sobolev class, but I believe that Sobolev introduced this W just to commemorate Weyl. But this is called Sobolev classes, but so mixed Sobolev class with parameters R and P. So this is this quantity. This is this set of functions. F can be represented in this way. So phi is function like this. So it is actually a unit ball in that space. And this is convolution with this kernel, the convolution with this kernel. So in a certain sense, phi is a mixed derivative of this f. Actually, it's a little, maybe let me make this remark just very briefly, because this one stands here. So what is the problem? Because, for instance, if you write, if you want to write like even that Cox-McCloskey inequality in a precise way, you cannot write just the norm of mixed derivative on the right-hand side, because if you take function which does not depend on one of the variables, you will get 0 immediately. But this does not mean that the error will be 0. So you should take care of this. And actually, this one technically is very convenient. This one takes care of all that stuff and makes all this precise and explicit. So this is the function class. And it turns out that those two classes are very close. So, and this is here. So this is the statement which says that if you take any Cubature formula, with this very natural assumption actually, if you take any Cubature formula, then for that Cubature formula, the arrows for this function class and for this function class, what means for this function class of characteristic functions, these are of the same order. And at this point, we are interested mostly in the order results. So we are not talking about explicit results with explicit constants. So in that sense, these two classes are very similar, very similar. And thus, you can look at this class and see that this class is a very, very specific class, because when we define this class, we have these two parameters, R, what is smoothness, and this one, it is, in this case, P equals 1. So we have a variety of these classes, but discrepancy is associated, and in this very, very close way, to this one, to this particular class. So, and these are some remarks about these classes. As a matter of fact, these classes are very closely related, univariate case, to the class of functions with bounded variation, and this multivariate generalization to the class of functions with bounded variation in the sense of Hardy-Vitali. So, and this definition goes back to the beginning of 20th century. So these classes in this sense are very, very, very old. So another function class. And this function class will be close to the periodic. And in the periodic case, as you remember that parameter R, smoothness, was just exponent in that representation, Fourier representation of the function. So clearly, it doesn't matter for us either to take this R to be integer or to take this R to be a real number. It doesn't matter. But in this case, it will matter, and R will be an integer. So we defined the following class. So, and this dot here stresses that this is a different class, but actually it's very close. And in this case, we do not assume that it is 2 pi periodic. So this, in that case, it will be very close analogy to the discrepancy. So what is that class? Now we define the set of classes in this way. So remember, in the definition of that class, it was a convolution, but it is kind of integral operator, in a sense similar to convolution, but not quite. So phi stands here, and we introduce function like that. So, and this is a key function in our consideration. So let's look at this. What is this function? So plus means this. So it is either the argument which stands here or 0. So if you look at this, let's say R is equal to 1, because this will correspond to the discrepancy. So what is that? That means we have 0 here, and the whole this quantity either 1 or 0, right, from here. So that means it is a characteristic function, and this is also 1. So this product is just a characteristic function. And characteristic function we are integrating here with respect to t. So what means if t is small, this is 0. And if t is greater than xj, it is 1. So that means that this integral representation is just we take function which is bounded in LP norm, and we integrate with respect to each variable beginning with xj to 1. It is known, it is clear that in this case, with this kernel, it is more convenient, because in this way, we can represent function f applying this kind of operator with r equals, for instance, 3, in using its third derivative. So we should integrate not from 0 to x, but from x to 1. So this is more convenient way. So this is the kernel. But again, let me stress that it is clear that when r is equal to 1, it corresponds to the case of characteristic functions. So now let's continue with this and establish one more relationship. And this relationship will give us a way to define the R discrepancy, what is the generalization of discrepancy. So for this function class, what I just defined, let's consider the following quantity. So we define this like an arrow in this case, and let's take the supremum. Again, this is what we have already done with other classes over this function class. Then, because of that representation with the kernel, because it's integral representation, we can write easily, because we are taking supremum over f. This would mean taking supremum over phi. But phi is bounded in LP norm by 1. So just by duality argument, you get immediately that this will be the norm of the other multiplier in the dual norm, so in P prime. So now let's look at this quantity, because this is exactly the one what we introduce at the R discrepancy. So this R stands here, and this C is a set of points, and lambda is a set of weights. M is kind of redundant here because M is the number of points, but this is very important, so we stress it here again. And D is a dimension. Again, it's hidden here too, but anyway, they stress that M and D are important parameters. And P prime is the norm in which we are looking for that. So let's again look at this and see in that particular example of R equals 1, what is that? So let me return back one slide. So we look at this function. So this is the one. So this is just normalization parameter. But what is important is this. So again, it is a characteristic function. And with this parameter like that, tj minus xj. So if you look at this, this cj stands here, and this is the norm with respect to t. So if you take this sum, it is clear that it is non-zero, it is 1, when the coordinates of these ones are less than coordinates of this one. So in this case, this is exactly a characteristic function with parameter t as the biggest, the upper right vertex of this characteristic function. So this is exactly a characteristic function of the corresponding one. And what is written here? This is the integral, and this is the corresponding Cubature formula. So when lambda mu, all of them are 1 over m, it will be a classical definition of discrepancy when p prime is equal to infinity. But it is, again, now it's more clear somehow why it is related to those classes which we just discussed before. Because when p prime is infinity, then p is 1. So, and that is like w, that was mw11. So the classical L infinity discrepancy corresponds to the classes which are defined in L1 norm. And what is the advantage of this? So R can be any integer here. So it could be 2, 3, and so on. So basically these are definitions. And here is the remark. So the remark which I have already made. And this is one more notation. So if lambda is the specific, so all are the same, we introduce this notation. So we kind of drop this lambda and just write m, and this means that if it is dropped, that these are the same 1 over m. And now here is the theorem, which actually says that these classes and these classes, which we defined, it should be periodic here. There are other classes, but let's say periodic case. These are equivalent in the following sense, but let me make this remark here. Even the previous result, what was proposition, we had for any Cubature formula, we had the same arrow in the sense of order for those classes. In this case, we claim that for these classes, we have the same minimal arrow. The difference here is the following, that we can minimize over the knots and over the lambdas. But we will be talking mostly about lower bounds. And for lower bounds, it is clear that if you prove the same lower bound, when we take infimum in addition to knots, also infimum over the weights, this is stronger. Because we allow more. We allow to use any weights, and if we prove that we cannot do better, that this is stronger than just with fixed weight and optimizing over the knots. And this will be actually the general spirit of some of these results. But anyway, from these points of view, these classes and these classes are the same in this sense. So if we get some results for Cubature formulas for these classes, we can transform this immediately to the lower estimate for the R discrepancy. These are general remarks which are basically to the following effect, that when we do this, one is kind of traditional, and this is written here for smoothness classes and approximation theory. We usually look at the whole scale. It was historically, it was long ago, maybe like the beginning of 20th century, like when de Laval-Poussin worked on this, and they proved for some specific classes like Lipschitz 1 or whatever. But later, after that, people were working not only in smoothness classes with different smoothness, but also in classes with modulus of continuities and so on and so on. So very, I would say, tiny scale of that. So this is one remark. So the kind of nature of to consider the whole scale, not to confine ourselves just to one specific R. But this makes the problem more difficult, it is clear. But anyway, also, and basically this is the point, that we can see how this R, the smoothness, how this may affect this discrepancy. So from this point of view, we can say, if the previous approach is discrepancy, says you if this set is good or not, using just one R, one specific R. But now we can look at the set, for instance, like van der Korput set of points. And we know that it has very good discrepancy in L infinity. But this is for R equals 1. So next question we can ask, is it good for, say, R equals 2, 3, 4, and so on? I will not go into details about that, but we'll make some comments. And now some historical, I would say, survey of this. I will begin, it will be not very complete, I would say, history, but anyway, some major steps of that history I want to present. And I don't think anybody have already presented at this conference, so let's go over that. So the whole this story began with a little bit different setting, I would say. In this setting, we considered not like in the discrepancy problem, we have n fixed. In my notations, m fixed. So we have m points, and now we are optimizing in the sense of discrepancy of these points. But points are fixed, and the configuration, optimal configuration, may depend on this m. But the original problem was we take a sequence of points, and this sequence is given. And now we look at the discrepancy for first m. So how they behave the first m. And this is univariate case. And the conjecture of van der Korput was that this lim sup, so this one behaves like that. So now we know that it actually behaves like this product behaves roughly like log m. But at that time it was not clear. And the first step was done by Van Aard and Ehrenfest, and she proved that this holds. So what means this product increases at least as iterated log divided by triple iterated log. But again, as you can see, this is very far from what we know. But the point here was, and I think the first who noticed that was Roth. He noticed that this problem for sequences in univariate case is equivalent to the discrepancy problem with m fixed in a two-dimensional case. So that means that was direct way to get results in this problem, and that probably was part of the motivation for Roth to look at this problem. And now there's further results, and we immediately at this one, and in order to formulate this in better way, I look at this infimum because we will be talking about lower estimates, so this is infimum. But let me stress this again. So when we are talking about discrepancy, this classical discrepancy, it could be in different norms, like this NLQ norm. And what is that norm? Remember, when we defined the classical L infinity discrepancy, we took a supremum. So in that case, and that was absolutely obvious that taking supremum over that parameter or taking supremum over the function in the class, this is the same. But when we take this LQ norm, it's not anymore a supremum over class, but kind of average over the class. But in this case, it is easy to introduce the measure on that class because it's one-to-one correspondence between parameters and this. So we parameterize and introduce measure on these parameters and write LQ norm. So this is another topic, I would say, in approximation theory. When you consider, instead of supremum over the class, you consider some average case. But in order to consider this average case, you need to introduce a measure on functions. But this is non-trivial problem. But in this particular case, it is trivial because all functions are parameterized by just points, and which allows us to use the Lebesgue measure. This one point and another point, if we consider that more general setting, when in addition to knots, we can optimize over the weights, then will be an extra infimum here. So when we are proving lower estimates, and this is the remark what I have already made, then those results would be, at least formally, would be stronger than this, if clearly the right-hand side is the same. So, and that was the first result in this direction, which is sharp, and this was what proved by Roth, and Michael even gave a proof of that. And the L infinity case was the first result by Wolfgang Schmidt. He proved this, but only in two-dimensional case. And you know now that this is a big problem, and let's talk a little bit more about that problem. And one more success in that was done by Wolfgang Schmidt. So in d-dimensional case, he, I would say, extended the Roth inequality lower bound for Q like this. So it is clear that the smaller the Q, the stronger the inequality, because LQ norms, they are monotone. The smaller the Q, the smaller the value of this norm. So if we have that same right-hand side, and we can see that this is the same, except the constant may depend on Q. So if we have this for Q equals 1, it would be ideal. So it will be the strongest result in that scale. And for Q equals infinity, it is trivial. For Q greater or equal than 2, trivial, I mean trivial corollary from Roth's result. And for Q between 2 and infinity, it is a direct corollary of the Schmidt, of the Roth result. But for Q less than 2, it is an improvement, because it is a weaker norm, and we have the same lower bound. And for L1 norm, we have this. And as you can see here, D stands here for any D, but this is actually sharp for only D equals 2. So it's also an open problem. We don't know what is the right behavior in L1, and we don't know what is the right behavior in LQ, because what is written here is D minus 1 over 2. So we know now that it's not the right thing, but we don't know what is the exact order. As a result of all those developments, and I would say that maybe the beginning of 80s, maybe the end of 70s was a really active time in this theory, with discrepancy. And Beck and Chen, these two were very active in that area. And in the book, what they published, they formulated the following conjecture. And they named this conjecture as an excruciatingly difficult great open problem. It's another question, but this was 1987. This is history. So this is whatever he says now. This is his name on that book, and this is published. And yeah, so this is it. Yeah, I mean, I remember that discussion. We had recently a conference in California, in Palo Alto, and we discussed a lot of these kind of questions. And the main topic was discrepancy and this and that. So there are different conjectures now about that, but I will give an argument which I shared on that conference too, that I think that this is the right formulation of the conjecture. But anyway, I mean, this is a different story, and the problem is still open. There is, and that was really big progress in this problem from that time when the problem was formulated, and I would say that this result kind of revived interest in the area, because that was really breakthrough, the new technique and new result. And here is the result, and Mike will discuss this in detail, and we'll continue to discuss. We'll give some proofs. He will not be proving this, but the related stuff, and the technique is, I would say, more or less the same technique as he uses for small ball inequalities and they use for this problem. But if you look at this, what is done here? As I said, the case when this eta is equal to 0, this is a direct corollary from L2 estimate, which was proved by Roth. And they did this. So they proved that there exists a positive number. It may depend on D, but anyway, it is a positive number, that this is the right lower estimate. And now the question is, and this is what basically two major conjectures do not agree with. One conjecture is that this eta D should be 1/2. So it means it should be D over 2. D over 2. Another conjecture, and that conjecture belongs to Beck and Chen, that this eta D should be D minus 1 over 2. So one is stronger, one is weaker, but we don't know. We don't know. Now, as to lower bounds on R discrepancy. And here is just notation. So there are two variants. One variant, we just keep this R as a new parameter and consider an analog of discrepancy, what means all the weights are the same. And another thing, we take infimum not only over the knots, but also over the weights. So clearly this one is smaller. So and again, if you prove the lower estimate for this one, we get immediately the same lower estimate for this one, for this quantity. And as to this connection between discrepancy and Cubature formulas, it is a little bit strange, but there were different groups of people who worked on the Cubature formulas and those who were working on the discrepancy. It was some overlapping, but not that much. And I would say the first time, and this was a corollary of the results for Cubature formulas. And Viktor Bykovsky in '85, he proved this. So it is an analog, I would say, to the Roth's result. But in a sense, it is stronger because in two directions. One thing, we have 0 here, that means O, that means we are optimizing over the weights 2, this one point. And another point that we have R here. We have R here. So this is proved for any R, for any smoothness. And the corresponding generalization of result by Schmidt, but that result which is for LQ is this one. So again, it is in that same spirit, but the proof for Q is very different from the proof for for Q equals 2. And actually, it's required some estimates for volumes of the coefficients of trigonometric polynomials, multivariate trigonometric polynomials, which are bounded, say, in L infinity by 1 or something. So this was more like geometrically involved, I would say. And in particular, I formulate this theorem here because this result is a corollary from the following theorem, which gives the lower estimate for Cubature formula. So now we take classes like this, WRP, and actually that Q will be dual to this P, but it doesn't depend on P here except this constant. So this is the lower estimate for the Cubature formulas, and it can be transformed into that lower estimate for that R discrepancy. As to some further results, I think it is interesting to discuss this one. So if we take R even number now, so this excludes R equals 1. So this is a classical discrepancy. So if you take R discrepancy, but R is an even, so I would say half of this case, so all even. In that case, we can prove this. So this is exactly like Beck and Chen conjecture would suggest if we extend that conjecture. Because in the case R equals 1, that conjecture states that it should be m to the negative 1 and this log to the exponent d minus 1. But in case of even integers, it is proved now. So we know that this is the result. And I would say that as to approximation theory results, at least I do not know any results in approximation theory of the nature that the arithmetic nature of smoothness, in this case R, either odd or even, would affect the rate of approximation, this law. Clearly R affects, but this would, if the conjecture, what some people believe is true, that means it's d over 2, then it would mean that in this case, for r equals 1, we have d over 2, and for r equals 2, it is different. It jumps by, 2 times this exponent for the log. So this is why I believe that this is the right thing. And this conjecture is actually to that effect. It is stronger than that one because it contains r here and this also this O, optimal in the sense of weights. But anyway, I think that, but now we don't know what is the right answer. So anybody is kind of eligible to make a conjecture and see what will happen. And another two, this, as I said, these two things are very closely related. And in a sense, these two conjectures are stronger than the previous two because other are corollaries from this. And again, when we are talking about L infinity, we have this one. So this conjecture is closely related to the previous one because we are talking about class which is defined in L1 norm, what corresponds to L infinity is a classical discrepancy. And this is the one which I would say corresponds to the result by Halash. In that case, this one, the class which is defined in L infinity, and we claim this. So in a sense, what is interesting here, in this case, the conjecture says that when we go in terms of R discrepancy from this Q, the LQ norm of that, to infinity, we have a jump from d minus 1 over 2 to d minus 1. But this conjecture says that when we go in other direction for with Q approaching 1, we have a continuous function. It's still d minus 1 over 2. And to my personal opinion, just working with this stuff, with these classes and Cubature formulas on these classes, I think that this one is more difficult than this one. Because usually this class, MWR infinity, is more difficult than this class, because this is L infinity norm here. And the corresponding remark, and this is what I basically have already said, that this corresponds to L1 norm for the discrepancy function in these terms. And now let's talk about upper estimates, because, and this is what I said, that the most interesting at this point for us is lower estimates. But upper estimates are also very interesting, and here is a brief history of the Cubature formulas for upper estimates for these classes. So, many people attribute the beginning of this to Nikolai Mikhailovich Korobov, who worked on this in the 50s, at the end of 50s and 60s, and he built the Cubature formulas, which are known now like quasi-Monte Carlo Cubature formulas. But these are purely deterministic Cubature formulas. They have nothing to do with stochastic or Monte Carlo approach. But that time, Monte Carlo method was so popular that everybody wanted to wrap up his results in kind of Monte Carlo. So, but they provide very good estimates, and Korobov proved this. And if you look at this, you see this RD here, this exponent. So R stands here, R greater than 1, and D instead of D minus 1, so this is one thing. And then in 59, Bakhvalov improved this to this one. So replace D by D minus 1. This was done by Bakhvalov in this case, in G equals 2. He proved this estimate, what is optimal. What is optimal? Now we know this, that this is optimal. And he used the following, I would say, particular case of those formulas which are called now quasi-Monte Carlo formulas. These are Fibonacci Cubature formulas. So these are of this type. They are built in that way. So mu is a running parameter, and BN is a sequence of Fibonacci numbers. So, and this goes like step by step, and with the step equals 1 over BN, or 2 pi over BN. And the second one is kind of jumping, because we have fractional part of mu multiplied by this. And this is a big number. So big number, I mean less than 1, but this big number. So when we multiply by mu, this is this one kind of jumping. But it turns out that these Cubature formulas are very, very good. And if to make connection to, for instance, Dmitry Bilek talk, he discussed the case of Cubature formulas, not Cubature formulas, but for discrepancy purposes, when this number is just a rational number. For instance, here we can put this alpha here, but in that case, these Cubature formulas will be much worse than these Cubature formulas. So what we did recently with my graduate student Ray Yu, that those Cubature formulas with alpha, this irrational number here instead of this, they would have the property of saturation. So when R goes up at R equals 2, or these formulas cannot do better than the error m to the minus 2. So in that sense, these ones are much better. And again, this is an example how this more general point of view of this arbitrary and general R gives us a way or criterion to understand which Cubature formulas or which sets are better and which are not that good. And the breakthrough in proving optimal Cubature formulas for these classes was made by Kostya Frolov, and that was 1976, the first publication in Doklady, and he proved this. But in order to prove this, he invented absolutely new principle of building these Cubature formulas, and those Cubature formulas were based on number theoretic approach, and Korobov also used number theoretic approach, but if Korobov used, I would say, elementary number theoretic approach, which was used basically or based on comparison of these numbers and just more or less arithmetical stuff, elementary arithmetical stuff. But as to Frolov, he used these irreducible algebraic polynomials and built the Cubature formulas on the base of that. And he proved this the best possible upper estimate. And that one was later on improved, extended to this case. And this is also known to be optimal. And also this shows that this conjecture, which gives us lower estimate, cannot be made stronger. So this is the strongest possible. And I think my time is up. So I stop at this point. And thank you very much.